Thank you, Graham. Good morning, all. Let me start by thanking the organizers for the invitation. So I was a little bit surprised that I got the invite, given that my work really has rather little to do with electrochemistry, even though electrolytes will make an appearance. And I suppose the common theme is, what I'm trying to do is bridge scales in a different context, and hopefully what I'm going to talk about today also has some lessons for applications to electrochemical systems. And I'll just start with a video which kind of illustrates a problem. If you have a molecular gas and you're trying to come up with a description of that gas which is hydrodynamic, there's a lot of problems that show up, right? So standard approaches for homogenizing molecular systems run into a lot of problems if you're not in a special limit where things just work. And then the question is, can you do something? And if so, what is it that you can do? So I'll start by motivating the approach by referring to a problem of fluid turbulence, which is arguably one of the oldest problems where people actually try to bridge scales. And then I'll introduce a framework, a very systematic framework for how you can actually model systems at different scales, which we call SPIDER. And then a couple of applications of that framework for both continuous case, or where we're really trying to upscale a microscopic model, and where we're trying to upscale so in one case, we'll talk about continuous systems. In the other case, we'll talk about discrete systems at the microscopic level. So as you know, weather prediction, used to be done by doing simulations, right? So now it's more and more machine learning, where essentially what you do is you put a very fine grid, in this case, if you're trying to model the oceans. And if you look at the resolution of the computational grid, it's basically 5 kilometers and above, where the relevant scales in fluid turbulence go down to easily millimeters or below. So there's not just 1 or 2 orders of magnitude difference. There's many, many, many orders of magnitude difference. Now, the governing equations, they're well known. So at the microscopic level, we know everything with a great deal of certainty. There is basically conservation laws, right? So for the mass and momentum. We'll make a simplification. We'll assume the density to be constant. So basically just have a divergence-free condition. It's not essential, but to make the story easier to digest. So basically, in both equations, there is a nonlinearity, and the nonlinearity is really the interesting piece of the mathematics that causes all the problems if you're trying to coarse grain. Now, the traditional way that's been done in fluids, at the very least, is you go from a very fine scale description where all the fields are resolved to a coarse description where the fields are not resolved, or at least some fields are not resolved, by splitting somehow the fields into means and fluctuations. And then if you do it in a very formal way, then you end up with technically 2 evolution equations, right? So you have an evolution equation for U, so that gives you the evolution equation for U bar and U prime. So you kind of forget about what happens with U prime, and for U bar, you derive an evolution equation and pops out a closure term that gives you all the trouble. Now, this is actually not a good way to do it, and I'll illustrate this a little bit later. Because if you think about the small scales, they live their own life, and they are not decoupled from large scales. In fact, they have to be coupled to large scales. So there is really a crosstalk between large and small scales all the time. So if you ignore the small scales, you are actually doing a bad job. Now, the nice thing about it is that even though formally small scales are described by infinite dimensional variables, in reality, that's not the case because you have dissipation at large scales. And the dissipation brings the solution from basically an infinite dimensional space to a space of finite dimensionality. But the question is, what is that space, right? And how do you learn that space, finite dimensional space, on which you want to model small-scale degrees of freedom? So, these are the closure variables in our case. So the proper model, mathematically consistent model, is that you have two evolution equations, one describing large scales and the other one describing small scales. And what you need to figure out is what is the closure, as well as what is the constitutive or evolution equation for the small scales. And for the turbulence problem, at the very least, it's not the boundary value problem. It actually turns out to be an evolution equation. Now, the big problem is not just how to find the functional form of those governing equations, but also to find the correct variables. And the choice of those correct variables is the least trivial part. So in fluid dynamics, there are basically two kind of, by and large, types of approaches. You can do temporal coarse graining, and temporal and length scales, of course, they're related. So, small time scales evolve quickly, large time scales evolve slowly. So there's a correspondence. And in this case, you can just derive what the closure term is. So it's basically the standard Navier-Stokes plus a closure term expressed in terms of the Reynolds stress tensor. And you could, in principle, say, well, I can derive the evolution equation, given that I know what that Reynolds stress tensor is. I can derive an evolution equation for it, and that's what it is. But it has its own closure term, and that closure term involves messy things that basically correspond to various correlations, up to triple correlations in this case in the fluctuations. And then, of course, you can say, well, of course, I can find how those evolve as well, but then that, of course, gives you an infinite system of evolutions that you have to truncate. And if you truncate it, that system becomes unclosed. So you have to close it, right? So the standard way to close it is basically kind of not even bother with this, but essentially to model the Reynolds stress tensor exactly, because that's the simplest way to do it, right? And the most popular way to do it is essentially to introduce a constitutive relation where you relate the Reynolds stress tensor to the rate of strain tensor through an appropriate dimensional constant, which is known as the eddy viscosity. Now, one of the earliest and most popular models is this Grigoriev model, which looks very, very simple, right? There is a Fencer, well, it's not just one, there's a class of Fencer models which essentially solve evolution equations to figure out, what the eddy viscosity is. But all of those models essentially use variables that are scalar to describe small-scale fields, and that's actually incorrect. But this is kind of one approach. So another alternative is to do spatial coarse graining instead of temporal. And things kind of look, nominally very, very similar. You also get a closure term that kind of looks similar. But in this case, it actually turns out that, this tensor is not a Reynolds stress tensor. It's actually a bit more complicated. And then you're trying to figure out how to close the system by essentially modeling the stress tensor again, in terms of the large-scale variables using mostly empirical considerations, more recently, scaling and symmetry arguments, and occasionally, which is not a very popular approach, using some formal expansions of the microscopic equations. Now, this is also not the correct way to do it because, as I mentioned previously, you really have to understand what the small scales are doing. You cannot just sweep them under the rug. So there is a decomposition of this stress tensor that turns out to be quite useful, which is due to Leonard, which breaks it up into three components. So remember I told you that the biggest problem in coarse graining is that you have nonlinearities, right? I would argue that quadratic nonlinearities, where fluid advects various quantities, is perhaps by far the most common one. So this is kind of the case that deserves the most credit. And for quadratic nonlinearities, the closure always, basically the closure term, the closure variable always comes in this form. So the three different components, L and C and R, are basically what they describe is the interaction between the large scales, the interaction for C between the large and small scales, and finally, the interaction of the small scales, okay? Now, if you think about small scales as being described by, let's say, so this R, it's again, the Reynolds stress tensor. So if you think about the Reynolds stress tensor as being an appropriate variable, which is suggested by a formal analysis, then you could generate a closed system of equations by basically looking for closures in terms of the large-scale variables and small-scale variables, and it makes sense to think about the part that just describes the large scales to be closed in terms of the large scales, and then the part that describes the scale interaction to actually involve both large and small scales. But there's a problem of, what do you do with the small scales? So to close the system, you actually have to come up with a subgrid-scale model. And I'll show you that in this case, what you discover is that it really needs to be a dynamical model, okay? So the evolution of small scales depends on both the small scale and large scale variables. So how do you actually do the modeling? So that's the big question. And this talk is related in many ways to both the talk that David Bortz gave and Juan Lei gave. But in David's case, basically there was no physics, or almost no physics. It was mostly data. In Juan's case, it was mostly physics modeling and very little data. And I'll argue that actually both approaches, they have weaknesses. So you have to kind of intelligently decide on how much you bring from the physics side and how much you bring from the data side, and that actually gives you a very nice framework. So basically, the question that we ask is, what do you do if the formal homogenization approaches, whichever your favorite homogenization approach is, or if that fails, what do you do? So the idea is we want to infer the governing equations for an effective physical theory. So the idea is to construct an effective physical theory, right? Which is explicit and interpretable. And if you use a neural network, that's basically out of the window. And the idea is to use as little physics for this as possible. So in this particular case, we'll mostly use symmetry. Okay. Now, where does the formal analysis comes in? So if you have specific domain knowledge, then that specific domain knowledge, as well as some formal analytical models, they're really instructing you, they're guiding you towards a right choice of relevant variables or effective degrees of freedom. Okay? So, and I'll illustrate this on a couple of problems. Now, think about an equivariant structure of a typical physical model. They all actually look roughly the same. So, if we, for instance, think about the equations of fluid dynamics, this is the incompressibility and pressure Poisson, Navier-Stokes. This is the equation that I've shown you for the Reynolds stress tensor. So the first two, every term is a scalar, right? So transform the same way for the second one. Every term is a rank 1 tensor or vector, right? For the last one, it's, in this case, symmetric rank 2 tensors. So all of those equations, they have one thing in common. All terms transform in the same way, making the equation symmetry equivariant, right? And symmetry equivariance, despite really not being particularly specific, turns out to actually carry a tremendous amount of weight. So if you forget about fluid dynamics, then just think about how you would discover equations of a physical model. So I would argue that not all, but many physical laws can be written in the form of, as David suggested, basically linear superposition, where the coefficients are whatever they are, and then basically you have different terms that transform in a particular way on the symmetry. Now, if you use typical symmetries, translations, and rotations, so translations essentially means that the coefficients are constants with respect to group transformations. So basically, if you have translational rotational symmetry, let's say in time and space, then they're going to be independent of space and time, right? And then the rotation reflection symmetry basically suggests that you have a constraint on the terms that they have to transform according to the same representation. And in particular, I'll actually require that the terms transform according to the same reducible representation, which actually gives you a very nice additional kind of knob that you can use. So at the end of the day, if you think about different irreducible representations of the same group, you can consider as many of them as you want to, which, however many you consider and which ones, again, is informed by what you want to get, by the physics at the end. It gives you several libraries of potential terms which basically define the search space, okay? Now, to give you an example, if you think about a fluid in 3 spatial dimensions, then the symmetries, for instance, could be, it's not the full symmetry group, but translations and rotations, right? The original variables describing a fluid, so we know that from microscopics, right? Pressure and velocity. And the corresponding differential operators are actually related to the symmetries. They correspond to the generators of that symmetry group. So what you do is you form derivative variables, or I'll just refer them to derivatives, going forward, which are basically the variables and their spatial and temporal derivatives. And then you use those to construct different libraries and truncate the libraries based on, so most of the time, basically just on complexity, but you could, in principle, bring in physical considerations, including how many derivatives you allow, what kind of scaling you allow to simplify things further. So for instance, if you're looking at the Stokes regime, low Reynolds numbers regime versus high Reynolds numbers regime, then you may or may not want to have various types of nonlinearity included. And that basically gives you, just to give you an example, here's a couple of libraries up to complexity 3 for scalars and vectors, okay? Now, turns out that this is not a full symmetry group. If you use a higher symmetry, you actually do better. So the actual symmetry group includes translations, rotations, which is a Euclidean group, plus the Galilean invariance. And if you use the Galilean invariance, there are a few changes. So the differential operators are now different. Some of the derivative variables are not allowed because of Galilean symmetry. And what you find is that the same libraries actually shrink by a factor of 2. Okay? And the size of the libraries is actually something that is not irrelevant. Now, I'm not going to talk much about this. The libraries are actually generated in a completely automated symbolic way. So you don't really have to guess what they are. Now, the 3 pieces of information that you start is symmetries, variables, and data, right? So these are different. So basically, data tells you, what the variables are on a grid once you've chosen what the variables are. The symmetries inform 2 different things. They inform what the reducible representations are and what the differential operators are. And then if you combine the differential operators and the variables, you get derivative variables. Now, if you process the derivatives according to the reducible representations, so essentially you start from low-rank tensors, you construct high-rank tensors, then do some surgery on those, you get libraries of terms that correspond to different reducible representations, okay? Now, once you have the libraries of terms, then you can actually bring the data in, and using the weak formulation, as David discussed, that's the right way to deal with this. You essentially convert symbolic libraries into linear equations. So once you have linear equations for the coefficients, then the remainder is, in principle, rather straightforward. In our case, we actually have done quite a bit of work on how the regression is done. I'm not going to go into a lot of details except for saying that the version of regression that we use actually yields many equations potentially from one library, not just one. So potentially yields all of the relations from any given library. Now, to put things in perspective, what WCND approach does that David talked about is it is less than a half of in terms of complexity and in terms of capability of the framework that I described. So somebody, a godlike creature, comes up and says, well, here's a library. Okay, so take the data, run sparse regression on it, and then out pops up really a scalar relation, right? So the approach really is not equipped to handle either with tensorial quantities, which we have to use, nor can it really deal with different representations, nor can it really discover multiple equations, and you kind of have to do it by hand, right? So if you think about machine learning being really an automated procedure, it's not kind of the way to do it. Let me show you a couple of examples of how this works. So this is the example that I promised. This is my connection to this community. This is the electrolyte driven by a Lorentz force. And this bright stuff is just markers that are used to visualize the flow. So we use this framework to discover the governing equations from experiment in the case of electrolyte. And this is another example so what you see here, those strands there, actually, it's called active. People refer to this as an active pneumatic. These are bundles of microtubules, and they're slid along by kinesin, and then they fold, and you get this what's called active turbulence. So we also figured out using this framework what the governing equations for this problem are, and the interesting thing is that if you use just physical modeling, first principles modeling, sometimes you get into a rut that you really cannot get out of, and you end up with a wrong model. And in fact, the community studying active pneumatics have used a wrong model for more than a decade to model a particular experiment that basically looks exactly like the data that we've used. And it turns out that the model is wrong. And the nice thing is that since the equations that you discovered, they're all, I'm not showing you any of those because this is sort of not the topic of this discussion. But if you look at the equations, you know how to interpret them too, so you actually understand what the physics is that they represent. Okay, so now there's a theme or a sub-theme of the workshop on discovering boundary conditions. Can you actually also discover boundary conditions, not just differential equations? And it turns out that in the spider framework, it's actually not that difficult to do. If you're close to a boundary, so there are two things that are different. One is that the symmetry group is different, right? So you can rotate around the normal, but not in 3D. And the other thing that's different is that you have an additional variable. So in addition to, let's say, the velocity for a fluid, you also have to include the surface normal. And the surface normal is a symmetry breaking term. So if you have a symmetry break in your problem, it's actually straightforward to incorporate this into the equivariant formulas. So for boundary conditions, that's how you do it, by basically including the normal as one of the library variables. By the way, I'll pretend that our boundary conditions don't involve time derivatives, which is typically what people do, but in principle, you could leave it in. So construct derivative variables in the same way, do truncation the same way, generate libraries, so you get, again, at the lowest ranks, scalar and vector libraries. And now, this library, the vector library, turns out it's actually not irreducible in 2 dimensions. It has to be split into 2 components, the one corresponding to the perpendicular component to the normal and the one corresponding to the parallel component. And if you look at the perpendicular component, it turns out that it's actually the same library as the scalar. just multiply by the normal. So you don't, these are not independent. You don't really have to consider this one. So there are two independent ones, this one and that one. And again, yes?
The question, is there any, just to tie this back to the start of the talk, is there any, in this library of functions, is there any notion of the fine and coarse length scale?
So not here. Okay, so in the libraries themselves, there is no reference to coarse and fine scales. These are encoded by the variables, okay? So it's the variables that define what the libraries look like. All the coarseness and fineness is, well, it's encoded in two places. It's encoded in the coefficients and it's encoded in the choice of the variables.
So
I'll get to that later.
So okay, maybe you come back later.
Yeah, I'll come. So I promise I'll come back to this later. Now, just to show to you that indeed this works, we've recovered both governing equations and boundary conditions for a couple of problems where you do have quite a bit of a scale separation. So one is the turbulent channel flow. So in this case, Rayleigh's number of order 10 to the 5. In the other case, for Rayleigh binary convection, up to Rayleigh numbers of, it's not shown here, but up to 10 to the 12. And one thing that I would like to say is that turns out that, oddly enough, for this problem, we actually tried both the spider framework and WCND, and WCND mostly failed at discovering the correct equations for various reasons that are probably a bit too involved to get into here, but it is a problematic approach. So let me go and talk about specific examples. So I'll start with coarse-graining continuous microscopic models. So think about two-dimensional fluid turbulence. So these are all movies. So this one represents the inverse cascade, this one represents the direct cascade, and this one corresponds to freely decaying turbulence. So all of these, they're evolving fields. This shows you all the data that we use for training, okay? So full resolved, in this case, basically means the resolution is something like 496 by 496. Now, if you look at the subgrid stress tensor, which is shown here, just a snapshot. Remember, you can decompose it into three components describing large scales, interaction, and small scales. If you don't look at
Sorry, can I ask a quick question here?
Go ahead.
What were the boundary conditions for these?
So in this case, it's periodic.
Okay.
Doubly periodic in both directions. So don't look at the structures, just look at the numbers. So L captures most of tau, right? So C is an order magnitude smaller, R is another order magnitude smaller. Now, this actually represents a problem for learning correct closures, because if you're trying to discover from data constitutive relations that involve quantities of very different orders of magnitude, if you just do it without thinking, you will never get them, okay? But there is a way to deal with that problem. Again, it's probably too much detail. If somebody is interested, I can talk about that separately. But what does the analysis tell us? So the analysis tells us that if you feed the data in, then this is the constitutive relation that you discover, okay? Now, so there are a couple of terms that only depend on the large scales, and then there's a term that explicitly involves the Reynolds stress tensor that describes the small scales. So now, I promised to get back to the connection between large and small scales. If you think about the coefficients, so the coefficients C1 and C2 in this case are parameters in the large scale model, right? So these are your coarse degrees of freedom. Now, what are the small scale or microscopic parameters? It's really, these things, right? So the microscopic viscosity, the coarse graining parameter, maybe other things. So there is a relationship between parameters at the fine scale and the coarse scale, and you can actually figure out what it is by using a combination of scaling, dimension analysis, and formula expansions. By scaling, what I mean is you run data, you generate data for different values of those parameters, and then you see how the coefficients scale. Okay, so it's a data-driven way to figure out what the dependencies are. Dimensional analysis and formal expansions, of course, are not. So to figure out why we actually learned the model that we did, it's useful to do a formal moment expansion. So if you take a variable phi and then coarse-grain it, so basically it's this integral operator, coarse-grain operator, right? For a filter with finite moments, you can actually write this as an infinite series, a moment expansion. And for a particular case of a Gaussian filter, this is what you find, okay? So you find an infinite expansion in powers of basically the standard deviation, right? But we don't really discover the terms, the high order terms from data. So the trick here is that you can get this expansion in the continuum space, okay? Now, if you're actually trying to use the model, you are never using continuum space, you're using discretization. So you never see high order terms, okay? And you have to do something. So basically you model them, okay? Now, if you actually do the expansion not of an arbitrary variable, but of those component tensors L, C, and R, what you discover is that the first term is just a leading order term in the expansion of L. The first two terms are the expansion for L plus C, and the first three terms are the expansion of L plus C and R. So really, there is a direct relation between the structure of the model that we find and this LCR decomposition. So this is really what we go with, okay? So that's the model that we've discovered from data. And it's applicable for discrete grids, okay? I'm sorry. Now, now we have a constitutive relation for the subgrid stress tensor. Where do we get, how do we actually know what the Reynolds stress tensor is, right? So you need that variable, and we need a constitutive relation for it, or an evolution equation, some sort of a governing equation that you can use to back it out. And what you discover is an equation that indeed is an evolution equation with 4 different coefficients that you again have to figure out what they are. Now, if you use dimensional analysis and scaling, then you find that C1 is just 1, which makes sense. If we use Galilean invariance from the get-go, we even wouldn't have to do it. We would have just gotten this automatically. C3 happens to be the molecular viscosity. C2 happens to have the sign that's opposite to the equation that's derived from first principles. Okay, so this tells you how bad you can get things if you just rely on formal derivations. And C4 is kind of the most interesting case. So the C4 actually turns out to have a dimension of 1 over time, and therefore it actually has to be a field, not a constant. Okay, so we don't have a dimensional combination that allows us to get C4 basically as a constant. Using Buckingham Pi theorem, you can relate that scalar to other scalar fields that can appear, and you can construct other scalars. So, this is the only really dimensional combination that has the right units. If you compare orders of magnitude, you find that it's the wrong one. Okay, but there are also all kinds of tensor invariants. Energy is one, but there are also tensor invariants that you can construct from symmetric and antisymmetric component of the rate of strain tensor. And then you basically have to learn a function, right? And that's perhaps not the most precise result, but this actually gives you a fairly accurate equation. Now, just to give you a sense of how that accuracy of that equation compares with the exact time derivative of the Reynolds stress tensor computed from DNS, this is the correlation function between the two, and for suitably small scales for coarse graining, that's very, 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 very close to 1. And obviously, coarse graining starts to break down once the scale on which you coarse grain approaches the scale of coherent structures in the flow of the vortices. So that's kind of expected. Now, by far the most important quantity that turbulence models have to predict is how much energy you dissipate. okay? If you get that wrong, you get everything wrong. So this is by far the most critical thing. Now, so it's determined by the energy flux between large scales and small scales, okay? What you care about primarily is the net flux, but local fluxes also matter. And it's basically computed from the average of the rate of strain tensor and this subgrid stress tensor. So this is the result from DNS. This is the result from the model that I've just described. And if you look at them, you will never see any difference. This is the leading, the best, the most accurate LES model that exists. And you can see that it really gets things completely wrong, okay? So this is dynamic Smagorinsky, which is kind of a fancier version of that earliest Smagorinsky model, which is kind of closer to this model than anything else. So they both get things completely wrong. Now let me at the end talk about what happens if you are dealing with discrete data at the microscopic scale. So this is a molecular dynamics simulation of a compressible fluid. We set things up, basically set things up in motion by making molecules initially move in different directions, and then things homogenize. And the question is, what's the right model? So the idea here is we need to generate continuous fields from discrete data. And discrete data is basically positions as a function of time, from which, of course, you can compute velocities and accelerations. And then what you do is you do kernel coarse graining. So in this case, it's basically spatial coarse graining, where the width of the kernel actually doesn't need to be very large. In our case, it's maybe a few multiples of the mean particle spacing. So if you think about fluctuations, statistical fluctuations, they're actually pretty large. And then you use those to generate continuous fields, in this case, density and momentum density. And these are kind of pictures that you get if you look at the coarse-grained fields. So one thing that you see is those ripples. Those ripples actually representative of compression waves. Now, here's a list of equations that Spider generates. So this is a work of Daniel Gurevich, who is actually currently a member of the math department here. And so one is the continuity equation, mass conservation. The other is momentum balance. And the last one is the Light-Hill's equation of aeroacoustics that actually describes those compression waves. Okay? Now, there's a whole bunch of things that actually are not physical equations. One turns out to be an identity. And the rest turn out to be spurious relations that all have this particular form. It's 1 minus rho times some function of rho in higher moments of velocity. So really, it's really all approximately equal to 0, right? Because none of those equations are exact. They're just accurate. So here Spider kind of cheats, and it multiplies two quantities that are small, this one and this one, to get something that's even smaller. And what actually that tells us is that we've actually made an incorrect choice of variables, right? So Spider involves a non-dimensionalization, correct non-dimensionalization, which turns out to be critical. And if you don't non-dimensionalize variables correctly, you end up multiplying small quantities. If you were to choose the right variables, that problem wouldn't happen. So final example that I wanted to show is it's a molecular dynamic simulation of argon. So you can think about this either low temperature or high pressure. And in this case, the system phase separates into a gas and a liquid phase. And the difference from the previous movie that I've shown you is that there's a lot of thermal motion that you didn't see in the previous one. So what do you do if you have thermal motion? So if you have thermal motion, you have to actually do both temporal filtering and spatial filtering to separate the different time scales. And the rest is basically works the same way. So with the exception that you compute like the mass density or momentum density using the mean variables, and then when you look at the stresses and the energy density, basically the analogs of pressures and temperature, you use the fluctuations. Now, this is actually conceptually, for those of you who are familiar with the Chapman-Enskog theory, there's a little bit of a correspondence here. Where again, in this case, you use the solutions to the Boltzmann equation to define the density, the momentum density and the temperature. But the difference is that, one difference is that, the way the coarse graining is done, of course, is very different, right? So in this case, it's average over momenta. In this case, it's average over particles. So this equation is actually scalar, right? There's a very nice paper by Livermore that actually shows that you cannot close generally a system that involves a scalar vector and a scalar. Okay, so generally that cannot be closed. It can only be closed under very, very, very specific assumptions. Assumptions where the Knudsen number is small and you're basically sitting at thermodynamic equilibrium. If either one of those two conditions doesn't apply, then this just does not work. This does. Okay, so I think with this, let me just close and thank all the people that have contributed. I mentioned Daniel before, and Mateos are the graduate students, and Brandon is an undergrad, and a very talented undergrad that's been working on this. And this is, for those who are interested, this is the code that's actually used to do all the calculations. It's called PySpider, and the work was supported by DARPA and NSF. Thank you all. If you have any questions, we'd be happy to answer them.